Hello, I am Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology, and in this video we will try to understand how to calculate current in 15 ohm resistance which is connected between the terminals A and B for this given network using the Norton's theorem. Now here in this case we will apply the basic steps of the Norton's theorem. That is, step 1 is removing of the load resistance and shorting the output terminals. Now here, if we are applying the step number 1 and if we are removing the load resistance and shorting the output terminals, then its figure will become something like this. Here we are keeping all resistances as it is. This is the terminal A, and here again this is another 10 ohm resistance which we will keep as it is. This will be the third resistance and so on. We are not doing anything, just we are removing the load resistance, and this will be the terminal B, and we are shorting the terminals. Here these terminals we are shorting, and whatever the current we have here, that current will be the IN, that is Norton's current. I will draw the remaining part of the figure, that is 10 ohm, this is 10 ohm, here this resistance is 8 ohm, here it is 6 ohm, this is again 8 ohm, this resistance is 5 ohm, and remaining part of the circuit will be something like this. Here if we are completing this figure, now we are in a position to apply the steps and calculate the current in the short circuit, which is the Norton's current. Now here, if we are planning to calculate its current, in this case we can use the nodal analysis method, mesh analysis method, direct inspection method, or any other. But here if we are using the mesh analysis method or direct inspection method, we have the 4 loops, 1, 2, 3 and 4. And that's why the calculation of the current becomes complicated itself. In place of that, first we will simplify this figure by converting this delta into star, and then we will calculate the current in that particular case. Because if we are converting any delta into star, it will minimize the number of loops in general. Sometimes may not be true, but here in this case for this particular figure it's true. Now here if we are calculating its simplifying this particular figure, this figure will be like this, because we are converting this delta into its equivalent star, and its star will be something like this. Here is the star. I will draw its figure. Here is the terminal A and this is the terminal B, and this is the short circuit in which we are interested to calculate the current. This is 10 ohm resistance, this is another 10 ohm resistance, and here it is 5 ohm resistance. I will draw first. This is 10, this is 5. Now 1, 2, 3, that is 8 ohm, 8 ohm and 6 ohm, these 3 resistances are replaced by its equivalent resistance, that is equivalent star. Means here its equivalent star, which I have shown here by dotted lines, by red color. Means here this is 1, this is second, and this will be the third star resistance. This will be the third star resistance. Now here value of the first star will be, it is, I will name it as R1, this value is R2, and this value will be R3. And then remaining part of the figure will be the same. Here this is the remaining figure which is the same, that is as it is. This will be the figure. Its battery is having 10 volt, which is plus and minus. Now first I will find out the values of the resistances which are R1, R2 and R3, and then we will substitute its values. Here if I am calculating the value of the resistance R1, which is equal to resistance R1, which is equal to Here this resistance R1 is this. Here it is connected between these two. That is 8 into 8 divided by, it is 8 plus 6, which is equal to 64 divided by 22. And the same value, if I am using the calculator, it is found to be 2.91 ohms. Similarly, the resistance R2, here is, this is R1, this is R2, here it is connected between 8 and 6, its value is 8 into 6 divided by 8 plus 6, which is equal to 48 divided by 22, and this value is 2.18 ohms. And finally, this R3 is equal to, again, this is resistance R3. Here it is connected between 8 and 6 again. This value is again 8 into 6 divided by, that is 8 plus 6, which is again 48 divided by 22, which is 2.18 ohms. Now we have calculated these values. I will substitute here. This R1 is 2.91. This is 2.91. This R2 it is 2.18. This is 2.18. And R3 is again 2.18. This is equal to 2.18 ohm. Now here, if we know the values of the resistances, now look at the figure, how many loops we have. We have the 3 loops. I will name those loops. Here, this is loop 1, having its current as I1. Here, this is loop 2, having its current as I2. And finally, we have, this is the loop 3, having its current as I3. This is the loop 3, having its current as I3. Now, I will use the direct inspection method, and we will calculate its current flowing through the short circuit, which is the Norton's current. In this case, this is the Norton's. In this current we are interested. If we are able to know the I1 and I2, then we can calculate this Norton's current, which is IN, that is current in the short circuit. I will name here IN, that is A to B current. Now here, if I am using that matrix, the matrix general format is something like this. R11, this is R12, here it is R13, R21, it is R22, this is R23, finally it is R31, R32 and R33. First I will target on the diagonal elements, that is R11, R22 and R33. R11 is the resistance which belongs to the loop number 1. This is 10 ohm plus 2.91 plus 2.18 plus this 5 ohm. If I am taking its addition, it is found to be, that is 20.09 is the first diagonal element, which is R11. Then here R22 is the second diagonal element, or second parameter. R22 is the resistance of the second loop, resistance of this loop, which is 10 plus 2.18 plus 2.91 and so on. If we are doing its addition, it is 15.09. This is 15.09 is the R22. If we know R22, then we will find out R33, which is the resistance of the third loop. It is 1, that is 5 ohm, plus R3 2.18 plus R2 again 2.18. Its value is 9.36. This value is, it is 9.36. Now we know the diagonal elements, and in this method only the diagonal elements are positive and remaining all elements are negative, and these are the unknowns, which are I1, I2, I3, which is equal to constants. Secondly, we will focus on the calculation of R12 or R21, which is the resistance between 1 and 2. This is loop number 1 and this is the loop number 2. The common resistance is 2.91 and that value will be minus, means it is minus 2.91 this will be minus 2.91. If we know the R21 or 12, then we will target on or calculate the value of R13 or R31, which is the resistance common for the first and third loop. Now look at, this is the first loop and here is the third loop. Means resistance 5 and R3, these two are common for loop number 3. And if we are finding its value, that is 5 plus 2.18, means it is 7.18, that is again minus. Means it is minus 7.18 is the value of the resistance, which is R13 or R31. Finally, we will calculate the resistance R23 or R32, which is resistance between the loop number 2 and loop number 3. Here, this is loop number 2 and here is the loop number 3. The common element is only one, that is R2, which is minus 2.18. Means it is minus 2.18 and this is again minus 2.18. This is the value of the impedance matrix. Now constant, if we are traveling with the direction of the current, there is no battery. That's why its constant will be 0. For loop number 2, again we are traveling with the direction of the current in the loop, then again its value will be 0. For third loop, if we are traveling with the direction of the current, there is one battery and we are traveling from the negative to positive, that is a plus, its value should be plus 10. That is the value of the constant. And if we know all these constants, then we can use the calculator and we can find out the current, that is I1 and I2 in this particular case. I will use the calculator mode, then I will go to the equation mode, that is 1, unknowns are 3, then first is 20.09 is the first value, then minus it is 2.91 is the second, then again its value minus it is 7.18 is the third, constant is again 0, then again it is minus 2.91, this is 2.91, then 15.09 which is again minus 2.18, again its constant is 0, then A3 which is minus 7.18, then it is minus 2.18, then third value will be, it is 9.36, then constant is again 10. Here if we are doing this calculation x, that is first value of the current, it is found to be, that is I1, this I1 current is found to be, this is 0.64 ampere, that is 63964 approximate, I will approximate it. Then I2 is equal to second value, which is 0.36 again, which is 0.36 amperes again. Then if we are looking at the third value, that is I3, this value I3, it is found to be, this value it is found to be, that is 1.64. This is 1.64 amperes is that particular value. Now we have all these values, that is I1, I2 and I3. Now we will calculate its Norton's current. Now here Norton's current IN, I will calculate it is from the A to B, that is modulus value, A to B, IAB. If I am calculating IAB, if we are calculating from A to B is a current I1 because this current is downward and I2 is the upward, because for this complete branch there are two currents. For this branch there are the two currents. I1 is flowing downward and I2 is flowing upward. That's why resultant current must be here Norton's current, which is I1 minus I2. And if we are calculating this value, I1 minus I2, if we are calculating this value, which is equal to I1 is, it is 0.64 minus it is 0.36, and if we are finding its value, which is equal to, here in this case this is 0.64 minus 0.36, its value it is 0.28 amperes. This 0.28 amperes is the Norton's current, that is current flowing through the short circuit whenever load resistance is removed and output terminals are short circuited. Now for the calculation of the Norton's equivalent resistance, we have to remove the load resistance. For that case we should not refer this figure. because if we are referring this figure, in that particular case there may be the short circuit come into the picture. That's why I am referring the main figure which I have taken at the beginning of this example, which is given figure. Now what we will do, for given figure, remove the load resistance and remove this load resistance and replace all sources, which is in this case is only one source, by its internal resistance, and redraw the figure and calculate the resistance between the terminal A and B. That is nothing but the Norton's equivalent resistance. For that case, something figure will be like this. Here it is A terminal, and then here we have, this is another. Then here this delta is already converted into the star and its calculations are done. I will copy the calculations from there. The figure will be something like this, which already we have covered. And here in this case, this is the resistance and this point is the B point. At the same time, here the source is replaced by its internal resistance, which is 0 in this case. Now look at this value, which is 10 ohm, I will take as it is. Here this 5 ohm as it is, this 10 ohm as it is. And then this delta convert, this short circuit should not be there because we are removing the load resistance I am taking from this figure, and its delta, this delta is converted into the star, and its calculations are available with me, which we have done in the calculation of the Norton's current for that particular case, which I am showing here. Now here the value of this resistance R1, which is we have calculated, which is 2.91 ohm. The value of this R2, which is 2.18, that is 2.18 ohm. And value of the resistance, which is R3, this is 2.18 ohm, which we have already calculated. Now from this figure, we will try to calculate, the short circuit should not be there. From this particular figure, we will calculate the resistance between the terminals A and B. Now I will proceed further. Now I will proceed further for this calculation. Now, here, this is point A again. I will take this terminal outside and this terminal outside because the terminals between which we want to find out the resistance, those terminals should be outside, otherwise there is a chance of the confusion. At the same time, I will take this B outside and I will shift this short circuit inside. That will become simple for the calculations. I am not applying any formula, just I am redrawing the circuit with modifications or little modification. This is the short circuit which I have drawn. This is 10 ohm, this is again 10 ohm. This short circuit is nothing but whatever we have from outside that I have shifted inside, that's it. This 5 ohm resistance I will draw as it is. This is 5 ohm, here it is 5. Then this, I will take this B terminal outside. I will take this B terminal outside. In that case, 2.1 will be something like this. That is 2.18 ohm. And here, this 2.18 will be here. This is 2.18 ohm. This 2.18. And finally, 2.91 will be somewhere here. This is B terminal. Here it is B terminal. And this resistance will be 2.91 ohm. Now here, looking at this figure, I will redraw its structure because it is a bit confusing, and from that particular structure we are able to find out its value in the better way. Now here is A point. I will take two terminals, which are these two. Here is one resistor. I am not applying any formula. I am taking in the structured way. These two, this is long wire. In place of that, I can bring these 2 points together. That is, these 2 points are together. Then here we have one resistance and second resistance. I will draw same as it is, nothing. I am not applying any formula. I am copying as it is, but just I am restructuring it. Here is between these 2 points, we have only one element or only one resistance, which is something like this. Then here these 2 points are again together, which is here. I will name the resistances that will minimize the chances of the confusion, which is 5 ohm, this is 2.18 ohm, and this is again 2.18 ohm, and here it is 2.91 and it is the B terminal. This is 2.91 and ohm and it is B terminal. Now here, whatever here I have copied, same thing, but I have brought in the systematic way, something which will minimize the load of calculation. Now I will do the calculation. These two parallel resistances will be replaced by single resistance. I will write the values and then I will do the calculation. These two resistances are in series combination, and that is 5 plus 2.18. Its value will be, that is 7.18. That parallel with the 2.18 is, that is the second value. And finally it is the third value, and this will be the B terminal. This is 2.91 ohm. Its parallel combination, 10 is parallel with the 10, that is 10 into 10 divided by 10 plus 10, that is 20. Its value, it is 5 ohm. And if we are doing the calculation of addition of these two, that is 7 is a parallel with 2.18, that is 7.18 is parallel with the 2.18. Its calculation, if I am doing, it is found to be 1.67 ohm. And then we are in a position to find out the Norton's equivalent resistance from here, which is something like this. That is, total calculation is the 5 ohm. This is 5 ohm is in series with 1.67, is in series with 2.91, that is 2.91. This total value is found to be 9.58. This 9.58 is the value of the Norton's resistance or Norton's equivalent resistance. Now we know the value of the IN, that is Norton's current. We know the value of the Norton's resistance. Now here we have calculated the Norton's current. Now we know the Norton's current is 2.28. Then the complicated network will be replaced by the Thevenin's equivalent network. This is last step will be something like this. Here, this is, and reconnect the load resistance which is removed in the first step. I guess here load resistance is of the 15 ohm, because this problem we want to calculate the current in the 15 ohm resistance. Here is the Norton's current IN, which we have calculated, and its value, which I will show here, that is IN 0.28 amperes. IN is 0.28 amperes. This RN is 9.58. And then we can calculate this load current by using current division rule or by using Norton's theorem, one and the same thing. That is 0.28 total current divided by Norton's equivalent resistance, that is 9.58, plus load resistance, which is 50. If I am using the calculator for that, it is 0.28 divided by 9.58 plus 50, and its value is 0.01139 amperes. If I am using it properly, this value is 11.39 into 10 raised to the power of minus 3 amperes is the value of the load current. It is the value of the load current which is flowing through the load resistance by using this calculation we have done using the Norton's theorem. That's all for this calculation. Thank you.